here, except that there's a lot of people that don't really know you.
Yep. All right. So all right.
But
Okay.
we're happy to have Timo Lahde, who will tell us about Lattice vector field theory for nuclei.
All right. Thank you very much for the invitation. I mean, it's an honor to be here on behalf of the nuclear Lattice EFT collaboration, of which I am part of at the Forschungszentrum Jülich in Germany. So the other members, which I can sort of introduce briefly here, are Eppelbaum and Krebs from Bochum, and Dean Lee from North Carolina State, and of course Ulf Meissner from Bonn and Jülich, and now also, we are also very happy to have also Gautam Rupak from Mississippi State University as part of this team of ours. Right? So the thing is that what I will be talking about today is how we apply this business with the quantum Monte Carlo technique to EFTs on the lattice for light nuclei, right? So the outline of the talk, sort of like the topics that I would like to go through a little bit here today is I will first give us some introduction to actually how we sort of set up the quantum Monte Carlo simulation, right? So I mean sort of like a brief introduction to the EFT for the nuclei, and then I will say some things about carbon-12 and the Hoyle state. Right, this is one of the things that I will sort of talk a little bit about, and then I will of course go on from this and say some things about how carbon is made, like in red giant stars, and from there I will talk a little bit, about this entropic scenario, sort of as to the fine tuning of this nucleosynthesis, right? And of course, then I will also sort of talk about what we are planning now to do, like in the near future, and this will sort of like involve also going up to silicon, with the same methods, right? So the nucleons are sort of placed on a lattice, right? So they are actually fermionic fields, right? So we are on a lattice where the approximate dimensions that we are speaking about are the lattice spacing, which is about 1 to 5 Fermi, like in that sort of bracket, right? And the size of the box is at least larger than 10 Fermi. In this, so this is largely the so the nucleons are sort of actually not resolved in this approach. They are sort of treated as sort of point-like objects in this approach. Right? So then of course the whole thing here is actually how we construct the interaction between the nucleons, right? So this business that is called the chiral effective field theory. So it goes back to Weinberg and other authors back in the 1980s. So the thing is that we have sort of like like a systematic expansion in the momentum of the particles, for example, right? So we have, for example, at leading order, so we would have, for example, like a 1 pion exchange interaction and some contact terms, and then sort of like at for example, at like next to leading order. So so this would be then sort of like interactions which are sort of like less important as the leading order ones, right? So there would be, for example, like a 2 pion exchange interaction and actually more contact terms, etc. Right, so it's sort of like an EFT expansion of the potential. Right? So sort of, like more systematically, right? So one could say here that, here is sort of like an overview of actually how this goes, right? So the thing is that at leading order, right, so there are actually two of these low energy constants that we have to determine, right? So there's the one pion exchange, and then there are actually two contact interactions, right? And then at next to leading order, right, so there are actually more contact interactions and right, so various two pion exchange contributions, right? And right, then at next to leading order, we first sort of find the sort of three-nucleon forces, right, which then also bring in further constants that one needs to determine, right? So these numbers are the ones that we have to determine in order to do our sort of calculations of the nuclei, right? So the thing is that at this order, so the thing is that up to now, these calculations have been actually taken up to next to leading order in this the chiral expansion, and of course we actually hope that in the near future we can also extend this to next to the third leading order, right? But right, so the thing is that the results that I will now actually talk about, right, they are actually done up to next to leading order in the chiral expansion, right? So first of all, sort of like at leading order, the sort of like the interaction that we find on the lattice, right, in this or basically these two diagrams, right? So we actually write it in this form, right? So there are actually two contact interactions, right? I could say that usually one would actually sort of write it in this form, right? So there are actually many ways that you can actually sort of write this, but sort of like like a more familiar expression is this one, right? Where you have like an amplitude that looks like this. So you have one pion exchange, and then you have sort of like another set of these low energy constants, right? It's called C0 and Ci, right? So in these two formulations are actually, exactly the same, given these like relations between the low energy constants, right? Yes.
So each time you go to the next order, you introduce more phenomenological parameter, you mean, or there is a way to derive this?
No, they are. The thing is that we get them from the two-nucleon system, right? So we do that as a fit, and then we can actually use the results, for the nuclei, right? So you have to first fix the constants here, right? They are, like in this approach, they are unknown, right? Undetermined by the chiral effective theory, right? Of course, if you can do things like, of course, they are in principle calculable. If you could solve, the full theory, right? But in this approach, they are sort of undetermined, right? So like in this EFT approach, right?
So there are phenomenological.
The answer to your question is yes.
Yes. All right. Okay. All right. So yeah, right. So the thing is that at this level they are free parameters, right? So the thing is that there is the thing that when I sort of mentioned this word improved, right? So it means that we do this sort of, for example, that you can smear the contact interactions with this kind of sort of form factor if you want. It's typically like a Gaussian, right? And you do this to sort of like decrease the lattice artifacts, right? So this I will actually talk about on the next slide, right? So so this is exactly now actually how we determine the low energy constants, right? So we actually, the thing is that we sort of look at the two-nucleon scattering, right? For example, here is actually NP scattering, right? So these are, for example, the phase shifts in the S-wave channels, right? So the thing is that if we don't do any of the smearing, right, so that we just say that we're just going to put these ones, to unity, right? So then actually what we get is this kind of a description that, the thing is that at leading order we are kind of the description is not very good, but then actually when we get to next to leading order, then we actually find that it's already much improved, right? The advantage of the smearing is that then the difference between the leading order and the next to leading order is much less, right? So this is why it's called an sort of improvement. The thing is that it means that you sort of like avoid, sort of higher order terms that are large, right? So you get sort of like a more well-behaved expansion, right? So the thing is that at this point we can then actually do calculations for more than two nucleons, right? Because this allows us to fix these low energy constants, right?
So just let me ask you, so by doing the Gaussian smearing, you effectively introduce the effective range and shape parameters?
Yes, exactly, yeah.
So numerically, do you have to tune the Gaussian to basically reproduce the effective range?
Yes, exactly, that's what we do, yeah.
Okay.
Right, so then
And
so now,
another question, so to
yeah.
put in the hard wall,
Yeah.
you just have the potential given infinity at R greater than
Yeah.
R zero?
Yeah, so the wave function actually goes to zero, like at the wall, right? So the thing that it's yeah.
But how do you implement it in the simulation?
No, it's this is only used in the. This is not a simulation, right? This is just actually solving the Schrödinger equation.
Oh,
right?
so this is not. So you don't actually do this numerically on the lattice?
No.
Okay, got it.
So see, the wall is not used in the lattice calculation at all. It's only used in this fixing of the low energy constants, right? So the thing is that then we do this. So now sort of comes the part with the quantum Monte Carlo, right? So now I sort of set up the theory, right? So now we can talk about the Monte Carlo calculation, right? Right. So the thing is that the central object, that if you want to calculate this correlation function, which we call ZA, right? So it's basically like it's the exponential of the lattice Hamiltonian, right? And this allows us to sort of to obtain the energy of the ground state, right? So this can be some arbitrary, but well wisely chosen trial wave function. We can have all kinds of sort of ansatzes for that. We can have, for example, standing waves, just and for example, alpha cluster wave functions, or then just like or whatever you sort of think might work well, right? So the thing is that after that we sort of you're right. So the thing is that you sort of like evolve this object then for like some extent in the Euclidean time, and after that you can sort of like extract the energy from the decay of this correlator. The thing is that it's only like the ground state which is going to survive in the end if you are like at a large enough time, right? So the exponential decay of this object is going to be dominated by the ground state, right? And the thing is that, of course, you can then also actually do, of course, if you need to calculate sort of like the expectation value like of an operator, for example, like for example like a quadrupole moment or this kind of things, then you can just sort of like insert it in the middle, and then you sort of take again the limit to infinite time, and then you get sort of like the matrix element of this.
Why not calculate the energy that way? No? Because it seems to be more accurate. It would be a variation of the estimate of the energy than from the slope.
This would actually converge faster, right? It converges faster than the.
See, that one seems to be more accurate, you see, because it would be a variation estimate of the energy. If he converges, you don't know what it converges to. But that one you know, it will have a variational bound.
That'll be for
Yeah, the thing is,
finite temperature.
this thing is only, the thing is that this is always going to be sort of like a little bit above, the real value like this.
I agree. I mean, if you do it right.
The limit
The variational just gives you that limit.
In the limit.
Yeah.
In the limit.
But
But if
I
it doesn't reach the limit, you see the second approach is suggesting it's more accurate.
The other one will be also an upper bound because you go from above down and you never go below.
I mean, this one converges exponentially fast to the right answer.
Which one?
This one. This converges exponentially fast to the ground state.
And the thing is that it seems to work very well, but of course if you have
The
some.
ground state is well separated
Yeah,
in the first
if there's a
exercise
gap.
stage,
Yeah.
and then you see
Yes,
the slope.
of course, yeah.
The slope is proportional to the particle number, so the bigger system, you see, the more trouble you have because the exponent goes very fast. Then you have lots of noise and stuff like this.
Right.
And so for that reason, you see the second one is much more accurate.
Well, how do you know? Because it just gives you an upper bound.
It's a variation approach, you see, and this is, what to believe in.
So I mean,
The other one you don't know.
What do you mean you don't know? I mean, if you at large time, if you go long enough, you'll actually get to the right
If you
ground
have a
state.
mixture of states, you don't know the slope exactly what it belongs to.
Okay,
You're right. So the thing is that we have actually, this is a long discussion. We can sort of talk about it later. So yeah.
Do you really converge to the stationary distribution in there?
Yeah, we can. Yeah,
Correlation time.
yeah. The thing is that of course we need sort of like an extrapolation, right? So the thing is that we can sort of, of course, the things that we can do this for something like.
In our business, we always reach pretty quickly.
Whereas usually that doesn't happen here, and of course, one of the reasons is that we have like a sign problem, that gets worse as we increase t, right? So that's why we have to sort of cut this off at some point, and then we have to sort of like extrapolate from there, right? So this we can also talk about later. If you're interested, for example, in the afternoon service. All right.
So related to this, what do you use for the psi-A's, or are you going to tell us what you use for the
Well, the thing is that I just gave sort of like a list here, right? So you can just.
Okay.
Yeah, we can talk about that. I can give you some examples, right? So this is yeah. So the thing is that this sort of like it illustrates that this is really like like a path integral, like in the nucleon fields, right? This object, right? That's why it's been sort of drawn like this, right? So the thing is that in that respect, so we do this thing, that we introduce and sort of like an auxiliary field, so that we actually decouple, these contact interactions, sort of, by the means of an this auxiliary field. And the thing is that, of course, you see now that if this would be sort of positive, then I mean, of course, the thing that you get sort of like a sign problem, right? You get sort of like like a complex phase in the calculation, right? And this is actually, the thing is that it's actually part of the reason actually why we do the calculation like in the way that we do it, right? So this is sort of like an overview of actually how we do the calculation. Now that we have actually sort of like introduced, this auxiliary field, right? So we have, so actually, first we do like a number of these time steps which only have this one, right? So we actually, these two terms are actually absent in this approach, right? So we have actually sort of this, these ones, and right then after that, sort of like a number of applications of these operators. Then right, we can sort of introduce the full operator, which then actually has like a sign problem, which increases sort of like by each application of this time slice, right? Right. So the reason for this is, of course, that the short range part of the interaction is sort of like repulsive, right? So this is also the thing is that if the lattice spacing is sort of too fine, right? So then right, this gets really bad, right? So the thing is that when you sort of choose the spacing, right? Then of course if you sort of take this actually very large, then of course the lattice artifacts are going to be actually gigantic, right? That's not what you want to do. But the thing is that if you also actually take it sort of like at the low end, right? Then you sort of kind of feel the short range repulsion, right? So then you get like a bad sign problem, right? So the thing is that this basically means that something like 2 Fermi, I mean, is sort of like optimal, sort of from like a calculational perspective, so to say, right? All right, and the thing is that this is actually calculated with the hybrid Monte Carlo sampling, right? So we do this sort of updates of the lattice, sort of, I mean, not random updates, but sort of deterministic updates, which sort of conserve the action, right? So you get like a relatively large acceptance rate, right? So the thing is that in this way you sort of generate sort of samples of the auxiliary field, and after that you can sort of calculate sort of what you want, basically, right? So the thing is that so I mean, of course, as this is sort of like a Monte Carlo calculation, then of course I should of course advertise the resources that we have at our disposal. I should sort of like apologize for the saturation of the picture over here. So the thing is that we are actually sort of we have this thing called Euclidean at Forschungszentrum Jülich, which is, I think it's in the top 5 sort of supercomputers at this time in the world. And right, we have some rather generous allocations, right? And then we also have some extra time, like at the Rheinisch-Westfälische Technische Hochschule Aachen, right? So the thing is that even though actually this is, the thing is that it looks like it's a lot less than, right? So So these nodes are actually like significantly faster. So this is also like a valuable resource, right? So the thing is that experimentalists, they always can show their equipment, and so do astronomers, right? So the thing is that as now we can also sort of brag about the resources that we have at our disposal, right? So that's also nice, I think. So then actually some of the results that we have actually gotten so far, right? So this here is sort of like a calculation of the ground state of carbon with this improved next to leading order interaction, right? This here is the lattice spacing that was used, right? So it's about 2 Fermi, right? So the thing is that here is sort of like at leading order, right? So this is actually done with sort of 2 different initial states, right? So the thing is that you have sort of the only difference is that the strength of this like approximate Hamiltonian has been actually varied, right? So we get actually two calculations that sort of converge to the same
But the projection
ground state.
time is only the internal one.
Yeah. Sorry,
The projection time refers only to the inner.
Yes,
time.
exactly. Yes, exactly. Yeah. So the thing that you can see that we can do something like here 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 steps after that, we are sort of killed by the sign problem, right? So this is the sort of like the limit that we have at this point, right?
So I get a question. So,
Yeah.
so the 3 and 4 body forces are turned up on helium-3 and helium-4?
Yeah. Exactly, right.
And then what
They
is
don't have 4, they have only 3.
Is that right? There's no helium-4?
They don't have 4 body forces.
So even with that 100 MeV cut off, for normal
There is, like right, so the thing is that there's the 3 body force, like is tuned to the triton, right? Then, right, so there is sort of like, right, so there is also like like a 4-nucleon term, which we sort of treat as a sort of like a modification of the 3-nucleon term. I will speak about that later. Right? So it's sort of like an improvement of the
So you put a 4 body
three,
interaction.
yeah, sort of by hand, right?
Well, I mean, with a renormalization scale of 100 MeV, I expect the many body stuff to really quite be necessary.
Yes, exactly right. So this is the thing, right? So it's sort of like like a compensation of like a lattice artifact, if you want.
So you've gone well beyond next leading order and the counting to have that operate.
Yeah, the thing is that it would appear at, I think, next to the 4th or next to the 5th leading order. Or this it's sort of like, yeah, but it's not the only way that you could. I mean, of course, you could also have sort of like like a smeared 3-nucleon interaction, and right, you could sort of like achieve the same thing.
Yeah, so I mean,
maybe like in that way. So
if I did a renormalization group flow on the interactions as I'm moving into the infrared,
yeah,
then the many body
yeah. So you would sort of
more important.
generate that kind of
Right, but
thing.
Then,
Sort
but
of.
in the counting, the strict hierarchy of counting that you outlined in the beginning isn't.
Yes, I guess you could.
To include the 4 body interaction here.
Yeah, the thing is that you could maybe say that. Yeah.
Okay.
I mean,
so
the
next question: what is the leading contribution to the variance correlator?
Sorry,
So
what's
the signal to noise problem when you turn on when you go away from Wigner symmetry.
Yeah.
What is
Yeah.
the leading intermediate state in the variance correlator?
Well.
So I understand this from lattice QCD, but for this
Yeah.
I presumably have 12 nucleons and I have 12 anti-nucleons as a thing contributing to the variance correlator.
Well, for carbon 12, you see you'll have the first excited states and they're in the range
they're not going to give rise to the signal from noise problem. They don't generate the variance. They're the things that dictate the convergence to the asymptotic energy, but not the variance. And so there has to be a lower mass state than.
I don't think you can talk the same language because you don't have backward diagrams here.
But you don't have vacuum. You don't have vacuum. The variance doesn't come from backwards in time. The variance comes from operator.
Yeah, because you
correlation
have
function
quark
operator
like quark
operator.
is in your case. It's here that's backward in time. You see here you don't have it.
No, that's not what generates the variance.
We should again.
All right, maybe we can.
Okay. Yeah, I'm just.
I'll sort of talk to you. I mean, like in your office later. I mean, about that. I'm actually very interested in. So, yeah.
See, looking at these results, you see
Yeah.
the time you went corresponds effectively to a temperature 10 MeV, because one of the T is the temperature basically, which is pretty high. So how are you sure that at that point, you see for carbon-12, you extracted the ground state properties accurately? Because the first 0+ is at 7 MeV.
Yeah. Yeah.
Right. So basically, the temperature is bigger than the energy of the first excited stage. Right. So I can think of this as being canonical ensemble.
But that's not dictating the temperature.
You see,
It's the
T
length
is
of
the
the time
inverse.
period.
No, but
T is the inverse temperature.
He doesn't have a full ensemble of
not.
functions.
Say it again.
He doesn't have a full ensemble of wave functions. He
No, I
only has
know.
one.
You see,
So-
but he has
But
partially that ensemble still. You see,
Well,
so
he has
it's not-
one wave function, and so that gives you,
See,
it takes you quite a bit
you-
there,
you-
and then with the evolution in time.
No, but still, this can be interpreted, you see, as a temperature, and it's pretty high.
If you had a full ensemble of wave functions, yes, but in this case you don't. So I think it's very different.
I'd like to
Oh,
hear an
I don't
argument.
understand this isn't a temperature, right? This is just the resolution, the energy gap that you can resolve.
Well, so it's 10 MeV. It's the same thing.
That's
You see, so it's pretty lousy. I would
That
say.
part is
It's
true.
not
Yes, but
Yeah,
That part is
you cannot build up contributions along
So if you think-
states that are orthogonal to the ground state in any case. So if you start with something that is the ground state, even if you project, even if you, I mean, suppose even that you have some, it's like considering a canonical ensemble but projected onto that symmetry state. So you never get contributions from the other.
No, but the same symmetry state, it's 7 MeV above. in this
So I
case.
guess the answer to your question is the original state must be pretty good. That's why.
Yes, no way.
Yeah.
Before evolution.
Well, the thing is that we can actually do this with, like a million, different states if we want, and we always find, the same ground state sort of consistently, right? So I would sort of think that this kind of shows that it works.
It's difficult to discern, how good your wave function is, because in electronic systems, I know if I have an excitation in there, it's very easy to say how big of the overlap that will be, and you can find that it's usually tiny, the Z next to
Okay.
it. How it is here, I have no idea. How, what's roughly your overlap of your ground state with your first excited state?
I think they simply declare victory at this point in that sense. It's a simple declaration we won, and they proceed. It's not
I think, well,
That's strategy, but one would like to know.
But they did say they cannot go further than this. So
They
This is what
simply
you
cannot
have.
go because of the sun problem.
that's right. That's right.
But then the question is how good this result is. You see, the fact that the sign problem prevented you to go further, it doesn't mean that this is a good result.
Well, it's what you can
See,
get.
it's,
That's
you
true.
got that, you see, kind of.
Well, the thing is that-
I think he has a point.
I agree. I agree with that.
You
Yeah.
have-
But this
no, the
what
thing
they
is
have.
that, of course, one has to do
I think if I go, you see, 10 times further, you see, then I know I have the reasonable resolution there, but they don't.
Fair enough.
Yes.
All right, so, but all right, okay, all right. So the thing, like which I would say, to this is that, all right. So the thing is that here is like, the next thing that I was sort of going to mention, right? So the thing is that we have also sort of, right, this is sort of like, the data here, again, for, the ground state, right? This is only like, like a leading order, right? So the thing is that, of course, we also then, I mean, of course, do, you know, the next to leading order and etc., but it's not shown here in this plot, right? So the thing is that here is then, like, you know, the data that we have for, you know, the Hoyle state, which is sort of like an excited state, right? And so it has sort of like, you know, the same quantum numbers as the ground state, right? So it's also like a 0 plus, right? So the thing is that, again, right, so now we actually, these ones that are here in sort of this thing that we call actually delta and lambda, right? So they actually correspond to these initial states where we actually use this sort of ground state, sort of like this kind of alpha cluster sort of ansatz for, you know, for I mean, you know, the sort of trial wave function, right? So
This is from data? This is from your calculations? You can actually look
yes,
at
yes,
The
yes.
alpha particle in comparison with the lattice constant.
What?
This is how big the alpha particle is, the ball in comparison with the lattice constant.
I'm asking,
But
Yeah.
I think this
I'm asking if these distributions have been extracted from the numerical calculation.
The thing is that this is sort of like, you know, the trial wave function, you know, that we use to. Yeah, right. So the thing is that it's what gives these two curves, right? You know, the blue ones here, right?
Timo, can you tell us one thing? I mean, the structure of the wave function is
Yeah.
dead. I think that his point is even stronger somehow, because in some sense,
what you said, the structure of the wave function
the
is.
structure of the wave function is actually the structure of the product of essentially three alpha particle
Correct.
functions.
Yeah.
So you find,
This
you know,
means
the
the
same.
chances that you're mixing in stuff here, and if you're not very careful, are
Yeah.
rather large.
But you know, the point is here, I would sort of say that, you know, the thing is that whatever ansatz you take, you always find, you know, the same ground state. Of course, it might be that if you just sort of, you know, kind of look at these points here, it's not very convincing. But of course, if you want, I have, you know, like a much.
But then how do you get the Hoyle state? In the sense that, I mean, the Hoyle state is essentially the structure of the wave function again.
Yeah.
So, I mean, in one case you have to project onto an excited state, in the other case you claim you project on the ground state. It's essentially start from the same function, more or less.
Right. So the thing is that.
I find very hard to understand. You don't seem to believe, but to understand.
All right. Okay. But maybe we should talk about that later. All right. Okay. Because I would like, you know, to finish this now. So sure. All right. So the thing is that I was also going to talk a little bit, I mean, about, you know, the Hoyle state here and the role it plays in, you know, the nucleosynthesis in the stars, right? So I mean, right, there is this triple alpha process which sort of depends, sort of, you know, exponentially, I mean, on this sort of difference between, you know, the energy of the Hoyle state and the triple alpha sort of threshold, right? So the thing is that experimentally, I mean, you know, the number is this, right? This is the number, you know, that sort of kind of goes into this exponential, right? And the thing is that, of course, then you could say that, well, I mean, of course, it's only going to change, you know, the temperature, you know, like at which, you know, this sort of like, you know, the sort of reaction is sort of happens in the star, right? So the thing is that, of course, then you could say that, well, I mean, how much does that really change, right? If we change, you know, the sort of the temperature at which carbon is formed in the stars, right? So the thing is that we can answer sort of from calculations of the stellar sort of like abundance of the carbon and the oxygen, right? So which is formed, I mean, if you sort of just actually change, you know, this value sort of sort of manually, right? So the thing is that, I mean, right, so this curve here is basically like it's the abundance of oxygen, right, which is generated, and this one here is sort of like the carbon abundance, right? So there's sort of like like a window here which is about 100 keV, within which you can sort of get like a reasonable, I mean, abundance of actually both, right? So the assumption is that you need actually both for life to develop, right? But this was now sort of just this kind of ad hoc change in this number, right? So we can see that, well, I mean, because is there any way that we could sort of relate this, for example, to variations in the light quark mass, right? So the thing is that so what are the sources of the quark mass dependence in the chiral EFT, right? So the thing is that the leading sources of this dependence would be, first of all, like the propagator of the pion and the coupling, and the nucleon mass, and then also some sort of implicit dependence on the pion mass in the counter terms, right? Right. So the thing is that of course we know from chi-pt that right, so there is a relation between the pion and the quark mass. So this means that if we know, I mean, the dependence on m pi, right, then we can also like obtain the dependence on the light quark masses, right? So the thing is that right, so then actually right, so this line here basically sort of summarizes the picture that I had on the previous slide, right? And the thing is that you're right. So the thing is that what we do is that we sort of like look at the sort of like like a perturbation around the physical point, right? So these quantities that I have actually now underlined here in red, right? Those we sort of those are calculable within the chiral EFT, sort of like our simulations, right? Whereas the other ones are actually somehow, I mean, of course, we need to I mean, obtain them sort of externally, right? So the perhaps the least obvious ones are actually these two. Actually, how how these numbers change if you change the change m pi, right? So the thing is that what we do is that we obtain sort of estimates for this by actually going back again to the two-nucleon scattering problem. So the thing is that if we actually now take the Lüscher equation, right, which sort of tells us basically, I mean, like at low energies, it sort of we can sort of differentiate it, and then we sort of get the how, I mean, the scattering length actually changes with m pi, and we can then use that to constrain these things that I call x3 and x4, right? So it was, I mean, these two unknowns in the formalism, right? So the thing is that here, I mean, again, everything is known from the two-nucleon problem, or then simply from chi-pt and some other sort of considerations, right? So the thing is that what we need in the end is sort of like estimates of actually how how I mean the scattering length in the S wave depends on the pion mass, right? So the thing is that in the end, right? So now, I mean, of course, I'm just going to show you actually results that we got from the Monte Carlo simulation, right? So the numbers here in the parentheses are that's sort of like the Monte Carlo error, and these numbers here are sort of the shifts in order to get from these two quantities, the basically like the sigma term and how I mean the coupling changes with the mass of the pion, right? So now we actually know how I mean the individual states sort of shift when you actually change the pion mass, right? So then we can actually say something about the generation of carbon in the end, right?
Can you go just back to the previous slide?
Yep,
So
yeah.
The ratio coefficients of the singlet inverse and triplet inverse, is it the same? Is the ratio of the coefficients of the triplet inverse versus singlet inverse variation the same?
Is the
ratio, so 0.69 divided by 0.34, is that the same ratio as in carbon 12? 3 divided by 0.4?
Yes, I believe so. They are actually, yeah.
Because you know from Lattice QCD what the first line is, right? Approximately now. We know what the whole first line equals.
All right, so actually these numbers now from Lattice QCD.
I know the box.
All right, sort of like the sum of this.
I don't know the sum of that, so that means I've constrained this.
Right, that's very interesting.
I also have constrained that.
Yeah. Yeah, right. Let's talk about that later because that's very interesting, right? If you have some further constraints on this, because this is, yeah. So the thing is that, of course, in the end, right, what we want to know is that right. So this is now, I mean, sort of like, the shift in this exponential, right? So we had this parameter, right? So now we can sort of put everything together and we get actually this result, right? So now the thing is that from this astrophysical consideration, right, so we can now actually sort of use actually this constraint, and after that we sort of get actually, I mean, right, so this is the relation that sort of like, like a variation then in the sort of like, a variation in the quark mass actually needs, to satisfy so that we don't end up like the moon, right? We end up like, the Earth, right? So there is this business, right? So here is no carbon sort of generated, right? So we end up in this scenario, right? If we go outside this bound, right? Right. So the thing is now actually, what do we know? I mean, about these two inputs from theory, right? So the thing is that so actually this is actually sort of like, the newest results from this. This is sort of like assuming that the low energy constants are basically given by this vector meson exchanges, and then you actually use the chiral EFT to sort of actually model that, right? So the things that we can see that the error bars are actually quite sort of, this is actually like sort of a theoretical error, right? So which attempts to take into account all of the uncertainties that go into that analysis, right? But still, I mean, of course, we can see actually, I mean, what we get using these numbers, right? This is sort of like the, well, what we sort of call now the end of the world plot, somewhat sort of, right. So the thing is that we see that the band here is basically like the constraint. It is our calculation, right? It's basically this line here, right? It gives the bands, right? And the dot is this thing from Berengut et al. These numbers for this. So the thing is that it's obvious that like a better analysis is needed. So if there is data from the lattice, for example, this would be, I mean, extremely helpful, right? But it seems that this is, the thing is that, of course, at this line, right, so there is absolutely no sensitivity, right? So then you would be always safe, right? Whereas, of course, if you go out here, then, I mean, like a tiny change, like in the quark mass, this would actually lead us into this scenario, right? So the thing is that then I would like to say like a little bit, I mean, about the upcoming results, right? So what we expect to do like in the near future, right? So we're sort of looking at oxygen, neon, right? And of course in the end, right, so we sort of hope to go up to silicon, right? And right, we also actually want to look at things that are actually sort of, well, for example, boron or nitrogen and these kind of things, that we don't just have everything in sort of.
What sets up the limit? It's silicon and not some other nucleus like calcium.
Yeah, well, it's the
why not magnesium?
computational time right now, I think.
You simply estimate how much time you need to calculate that.
Yeah, the thing. Well, I can maybe give you like a number, but the thing is that I could sort of. You mean like in core hours or.
No, but I'd like to know, you see, where the number 28 came from.
It's simply what we have actually done up to now. Actually, I mean, what we can actually do with the current resources. Actually, what we can get sort of like a reasonable signal for within the current resources, right? So the thing is that of course we can go. Yeah. I mean, of course, if we get I mean, of course, you have to stop, at some point, and then when you get actually CPU time, actually.
What is the scaling rate here?
It's about something like a to the 1.5 or something like that, right? It's sort of, it's relatively favorable, right?
So then going from carbon to silicon, it's not such a big increase. So
Yes, exactly.
It's 1.5, you see, you have something like.
Yeah, right. So we can go further, maybe. This is just where we have actually stopped. Yeah, right. So I mean, right.
So can they get factors of 3 in compute resources?
Yeah. That's roughly the, yeah.
It's a small factor.
Yeah, but I mean, tell that to the funding agencies.
Yeah, yeah.
We already did that, you see, so you see, we did carbon 2 years ago, 3 years ago, you see. Since then, they had enough time to do that. So factor
Yeah.
3, it was there already.
That's what it's all about, yeah.
So that's what I'm saying. You don't need an order of magnitude, you don't need tools.
Yep. All right, anyway, the thing is that I think I should probably end here, and it was very nice that there was so much lively discussion, and right, let's continue this in the fishbowl. I think there will be things to discuss.
Well, we thank you first.
All right, okay, great. Thank you.
And we have a bit of time for this.
Yeah, yeah.
Just a curiosity, what is the sign, average sign that you sampled in the worst case?
Oh, the worst case that we have gone to is something like positivity of sort of 0.07 or something like that. So it's pretty bad, right? 0.0.
7%.
Yeah, right. That's about what we can do. After that, things get really sort of rotten, and the error bars explode, right? So this is,
Well, it depends on how much computer.
Yeah. Well, that's of course a relevant question. Yeah. But this is right. So with that, we should be. So the thing is that, of course, in this case, the sign problem is much worse, right? Because some things that we may not yet completely understand. But this is, right? So we have actually sort of measured, the sign problem as a function of A, and it's not smooth, right? It's it has.
Shell effect.
Yeah. So the thing is that.
Go exponentially to 0 with A, no?
No, it's actually not that. It seems to be actually sort of.
Range.
When we go from, for example, up to this, right? It's not such a. Because it gets worse, but not dramatically, right? This is what we find, right? So you had a different.
It doesn't have to be exponential.
Oh.
If you're in intermediate times, it can be parallel.
Intermediate time, fixed time, you think.
You would expect it to be exponential with A, right? That's what you were.
I mean, it's exponential. at large
Fixed
times.
tau.
With the volume, with the hypervolume.
Okay.
Should go. No, it doesn't have to. It's only exponential at
Okay, at
very
large,
large, asymptotically
large,
large times. It
at
can
large
be
enough
parallel
times.
or
Yeah, there is
intermediate times.
this nice stability of this auxiliary field. For small time, does not go to much to zero.
The thing is that the thing is
Very
that
large in principle, it should.
there is a point where we sort of. Of course, when we actually increase, the time, right? There is a point where things sort of go
Break down.
down the hill, right? Sort of.
Okay. Do you have a question? No.
Okay.
Yeah.
Please, if you have. So.
Thanks again.
All right. Okay.
Thank you.
All right. Thanks. So I should press this now. So all right. Okay.